כי אז היה שוודיה, אבל אז היה עורך, לא היה נורא. לדעתי זה באמת מופיע. אבל לא חשוב, אף אחד לא יכול לדעת.
Okay. First, I wanted naturally to thank the organizers for bringing Jean-François back to be with us for at least 3 days here. And I'll try to continue with a historical perspective, although I wouldn't be able to go as far back as 1971, but I'll do my best. I'll do my best in maybe trying to give you a sense of the process of the joint work, and hopefully by the end we'll get to the results. So when I was visiting CORE in spring 2005, Jean-François asked me, what do I think about social discount rate? I had no idea what to answer, so I continued listening. He mentioned this document, a memorandum, which is written for bureaucrats, that is used by the executive branch of the US government, talking about cost-benefit analysis and how to calculate net present value of a public project. So a practical calculation says you have to take benefits generated by a project, monetize them, and sum up using some discount rate. On the other hand, he mentioned the work with Amrita Dillon, saying that if you use a good welfare function, then you could give a meaningful answer to what this social discount rate should be. Right? So the basic question is, when would the two calculations, one based on this just rule of thumb used by practitioners, and another one which could be rationalized using a welfare function, when would the two calculations coincide? And if so, what would the second one tell you about the first? Okay. He gave me the sense of what the question is, and naively I said, well, I'll go out to lunch and do some calculation on the board. Maybe I'll give you the answer. Little that I knew that calculation would take a little longer than a blackboard, and much longer than one afternoon. Direct calculation, in fact, became quite involved very fast, and we were looking for an indirect way to answer the question, which came to us January 2006, in fact, during a short visit to Yale, when both of us read the original of presentation of Kolmogorov's take on generalized functions and derivative of generalized functions. And in fact, the problem fitted exactly that framework, provided we could impose time invariance on the welfare function. Okay, welfare defined on a set of policies. Time invariance means that when you shift a policy in time, the welfare of that shifted policy is just an affine transformation of the unshifted policy. And the coefficients of the affine transformation depend on the length of the shift, of course, and not on the time when the shift occurred. And that property, in fact, was very powerful when used several times. It pinned down pretty much one of the coefficients of the multiplicative coefficient of the affine transformation. It had to be exponential. Then the whole problem was translated into, in fact, a differential equation for generalized functions, and we got the result that welfare could be represented as a net present value type. Okay, and as applied to overlapping generations model, in fact, the question was about intergenerationally fair discount rates. So we had to use several generations in that model. When we applied it to the classical macro model, we found out that if the proper welfare function is used, the relatively utilitarian one axiomatized by Dillon and Mertens in 1999, and then the rate of per capita consumption is the justifiable social discount rate. And it's quite, we were both excited because it was a highly abstract work which gave rise to a numerical answer. If you look at US data, then this rate will be equal to 2%, and that's what I told bureaucrats in Washington this spring. So the two, yes?
Can you explain the difference
compare something that is pretty specific and quantitative, meaning benefits and welfare. What are we to think about in comparing these two?
Okay, so in practical terms, when a public project is being considered, the benefits and costs of the projects are to be monetized. There are various difficulties associated, of course, with translating utilities into money, but in the end, everything is brought into single terms, monetary terms, and then one is to calculate the net present value of that project the same way as we calculate present value of a private project. And that's the rule that is being used in practice. The question is whether you can justify this rule or find rationale for that rule, okay? Because typically when an economist is evaluating a public project, he would look at a difference in welfare that would be generated by a project, okay? So the question here would be, when would the difference in welfare or derivative of welfare have the discounted form, okay? And if it does, what's the discount factor which will be implied by the welfare function we use?
My question was, what is the definition of welfare in your statement?
Okay, here we use the relative utilitarian welfare, which amounts to normalizing utilities of individuals between 0 and 1 and then summing up the utilities. Okay? And again, this welfare function was axiomatized in econometric in 1990. Okay? So to make the statement non-vacuous, we needed to verify the assumptions. First, time invariance was a very natural one, and it, in fact, is satisfied in a very wide class of common models used in macro, and that's the one that we used as well. Of course, it's a joint requirement imposed both on the welfare and on the model and on the type of equilibria that we're looking at. So the model has to be stationary, it has to admit stationary equilibrium, and then you use the appropriate welfare function. All these would be very natural ways to model policy analysis, very natural models that are currently used for policy analysis, and most of the macro people who you talk to, right, would start analysis of such a model with a stationary equilibrium, which we call balanced growth equilibrium. Okay, so the first requirement is kind of naturally satisfied in this world. Yes.
When you're saying time invariant, you mean just shift purpose?
Yes, as I said. Okay, so as I said, the time invariance means that the welfare of a shifted policy is an affine transformation of welfare of unshifted policy. And the coefficients of the transformation, the additive and multiplicative ones, do not depend on time, they just depend on the shift, the length of the shift. This, in the end, gives you this exponential form of the derivative. Okay, so the time component is exponential, and then there is some other component which can't be pinned down without knowing the model. Okay. So to make the statement non-trivial, or sorry, non-vacuous, we had to, of course, justify the assumptions. Differentiability appeared to be a hard one, and we had to come back again to that calculation of actually trying to calculate by hand, hand against the wall approach, derivative of welfare in a given example, in a given model. Okay, and of course that task, in fact, could be decomposed into two. At first, you want to look at the variation in policy and its effect on equilibrium variables in, say, the overlapping generations model, and once you've done that, you can look at how the changes in equilibrium variables would translate into changes of individual utilities, and then how to sum up these utilities into welfare and calculate the change in welfare. Okay. There were several difficulties that awaited us. First of all, these models have non-Pareto equilibria. There were some bad news established in the mid-80s saying that if you work with discrete time models where time starts at 0, it's impossible to do comparative statics. There's indeterminacy. However, Good news came somewhat later as we started working on in this project. Michaelis and Polymarchakis published a paper in 2007 saying that if you have an endowment economy with logarithmic felicity, logarithmic instantaneous utility, then as the time periods between transactions shrinks to zero, so you go from discrete time model to continuous time model, indeterminacy disappears. So bad equilibria are gone. There were some previous works on dealing or doing comparative statics in infinite economies, but they were not applicable to our case. I'll be maybe more specific about it later. Okay. So let's see what we had to deal with here. That's a classical model, and some variant of it already appeared in CAS in the 70s. So the timeline is the whole real line. So it starts from minus infinity, goes all the way to plus infinity. Model is stationary, so population grows exponentially at a fixed rate. It's an overlapping generations economy, so every agent lives for a finite stretch of time, for a limited stretch of time. And individual utility is a standard, as is standard in these models. The felicities of constant elasticity of substitution type. Individual, it's time separable, so you have, I never know where the button is. You have beta as the discount rate. And the typical individual, any individual in this economy born at any point in time will be maximizing this lifetime utility subject to the regular budget constraint that the value of consumption, that consumption stream, C of S, over lifetime cannot exceed the income. Wealth is composed of two parts. One is the wealth that comes from working, the wage income, as two components, the wage times the productivity. Productivity can change over lifetime of an individual. And the first component is our policy variable. It's the value of the endowment given to an individual born at time X when he's of age S. So our parameter in this model, omega xs, is, if you wish, the amount of apples that an individual of who was born at time X when he's of age S is given or taken away. Okay, omega in general, the sum of omegas is not restricted, so it can be a net transfer in or a net transfer out of the economy, or it can be pure redistribution across generations. Okay, so in the baseline, the baseline equilibrium that we'll consider, omega will be equal to 0. Then we change omega. We'll talk about perturbation of this endowment. And we'll have to see how all the variables, equilibrium variables, will react to that change. Okay. Here's the production side. It's called Douglas. That's how we started. Labor components, that will be labor available at time t, is growing exponentially with time. First of all, because population grows exponentially at rate nu, and secondly, because productivity grows exponentially, exogenously at rate gamma. So it's an exogenous growth model. Okay. There are investment firms in that model, and they use this capital accumulation technology, which is linear as well. Okay. So it's a constant returns to scale all over. And the utility is homogeneous of a fixed degree, so it's a stationary model, and therefore there is a hope to get stationary equilibria, balanced growth ones. Okay. It all looks very standard, and we were hoping to find some ready-made solutions, a characterization of equilibria of these models, but we couldn't find any, so we had to work hard and really write them down from scratch. And although it looks like a 2-page introduction of the model, the full characterization took 59 pages. I'll show you just a part of it, of course, and I'll try to highlight sort of where we went with it. So if you do characterization in small letters, dividing all the aggregates by the amount of available labor, LT, okay, and you translate the policy variable omega, normalize it to become E, that will be our perturbation now. It's the normalized amount of apples given at time t to an individual who is alive at that point in time, is of age S. Okay. Then candidate equilibria will be described, or can be described as a fixed point of the system. So if you guess an investment path, okay, you calculate capital according to capital accumulation equation from that. Given capital, you can calculate the output. Given all these variables, you can calculate the interest rate, or net interest rate, if you wish. From these, then you'll have enough information to calculate consumption, individual consumption, and aggregate consumption. And then from market clearing, or material balance, as Jean-François used to call it, you'll get a new value of investment. And if you happen to hit the same investment path you started with, here is a candidate equilibrium. Okay, so a necessary condition for an equilibrium that for equilibria that we describe will be a solution to this fixed point problem. Okay, so that's the basic system that we work. Okay. So among other equilibria, as I mentioned, our starting point will be a balanced growth equilibrium where KT is exponential and all the small letters are constant. So that's an easy one to look for. And out of this group, we'll look at a particular one where I over y is alpha. Okay. Now, let's look at the problem again. Okay, thank you. So we said that equilibrium function of time I should solve this equation, upsilon minus I is equal to 0. Okay, so if you just look at the most standard approach to that problem, you want to find out how your endogenous variable, right, a function of time, investment, reacts to changes in parameter E. Right? You have to use the appropriate form of implicit function theorem. And with the appropriate invertibility condition, you can claim that you can have endogenous variable I, equilibrium variable I, a smooth function of exogenous variable E. Okay. It looks nice, but unfortunately, it's quite difficult to find whether such operator is invertible in general in LP spaces. And one could use a standard way to proceed and try to maybe extend Sard's theorem, which was done probably since De Broglie. But when we were calculating all these derivatives, I suddenly realized that Jean-François was very happy about the fact that they all, at a balanced growth path, look as, or can be presented as convolutions. And only later, I understood that there was a reason for that. If you think about a spectrum of an operator, and here a derivative is an operator from one Banach space to another, right? By definition, what's a spectrum? It's the set of complex numbers such that that operator minus z times the identity is not invertible. Okay, that's just the definition of a spectrum, like a definition of an eigenvalue in a finite dimensional case. So if you take z equals to 1, okay, real number, then if unity is in the spectrum of the operator derivative of upsilon with respect to E, then we're in a bad case. We don't have invertibility, and we can't use implicit function theorem. Okay? Why? Because the derivative of f with respect to I is the derivative of upsilon with respect to I minus the identity operator. And it's that difference that we want to have invertible. Okay? So if we look at the spectrum of d upsilon di, and we find that unity is not in the spectrum, then we're good. Okay? We can use implicit function theorem. Now the question is, how do you find out what is the spectrum of this derivative operator? And here, what helped us was this formulation of Wiener theorem from spectral analysis, also suggested by a colleague from Colorado from the math department, saying that if you look at a spectrum of a convolution operator on LP, and it's given by a function, by an integrable function, then it's independent of P and equals to the closure of the set of values that will be returned by a Fourier transform. Okay. And in fact, the closure part is rather trivial. We just add 0 at infinity. 0 is not a point we're interested in, so all we cared about here was what's the range of the Fourier transform of this derivative operator du epsilon di. Okay? So now from then, the plan, it's sort of the very rough idea for the plan was clear. First, we have to make sure that this epsilon is smooth, okay, in both arguments, exogenous and endogenous. Second, we had to show, and we were sort of in the process of doing so, that du epsilon di is a convolution at a given stationary equilibrium GRE. And secondly, we had to show that the Fourier transform of that operator does not return 1, at least generically. Okay? Generically in the set of parameters of the model, and that's why we had a fully parameterized model. Then you really have a sense of, you know, what happens there in this space of parameters. Okay? So that was a very rough outline that we had in January 07, and took us quite a bit of time to get through all the details. And still, we faced another problem. Okay, faced another problem that if you perturb your parameter, your policy parameter E, and you get a smooth response of your equilibrium variable. Okay, that will still not be enough to show that you can calculate the difference in welfare. Why? Because although the equilibrium quantities are moving smoothly and maybe even returning back to the status quo, utilities might be proportional to changes in these quantities, but because there is an exponential growth of population, so there's more and more people, say, in the economy, you had to make sure that not only differences in equilibrium variables are summable, but also differences in equilibrium variables multiplied by an exponential are summable. Okay, so we had to have a much stronger restrictions on the response of equilibrium variables to ever hope to get derivative of welfare being finite. Okay, so one of the maybe natural solutions would be to say, well, let's restrict the types of perturbations in endowments that we start with, and let's look at perturbations in endowments that are both bounded and are summable when multiplied by an exponent to some power. Okay, so we'll look at the intersections of the two spaces, L infinity and what is called in the paper L1 lambda, where lambda stands for the exponential rate at which the variable converges. More precisely, right, a variable is in L1 lambda when it's in L1 once multiplied by an exponential to the power lambda t. Okay, so we had to do that. Look for lambdas in an interval that contains 0, of course, the baseline case, and repeat the previous steps. Okay. Already, if you look at the previous steps, you see that we'll have to have a different version of the implicit function theorem because the ready-made would not work. Here we work with a whole set of spaces as opposed to one particular space. And secondly, we would have to extend somewhat the Wiener result as well. Okay. That was quite a, right, and again, quite a bit of work. Going back to the theoretical foundations, and you know, in the end, we had this intermediate version, which was a core DP in January 2009. However, already in the summer 08, at the Society of Economic Dynamics meetings in Boston, Jean-François told me, you know what, this is still rather restrictive. You know, we shouldn't have the perturbation being uniformly bounded. It makes no sense. It's a continuous variable. There's no sense in restricting it. So I think we have to change the topology. Okay, despite my very active protest in doing so, because we almost had the complete paper. He said, no, you know, you can continue working on the models that potentially could be reused in the new version, but there is no way back. Okay. So what we had to do was to create a new space where our perturbations are to live. And later we figured out that some properties of these spaces were already described in the literature in the 70s and 80s. And motivation is to separate the control of the local end and global behavior of a variable. So the main motivation was to introduce this L infinity 1 space in which we wanted the perturbation, the change in endowment to live, right? So the locally it would be integrable, and all the integrals are uniformly bounded. Okay. So the idea was to describe, first of all, we needed all the tools that you know, the textbook properties of these spaces that LP possess typically, right? And our variable, our perturbation is a function of two real variables, the time and the age, okay? So it's defined on R2. And then the idea was to maybe write down these properties for functions from Rn to R. And then at some point, we started seeing that the proofs became too computational, and there are too many square roots, and it's ugly. So Jean-François suggested we should work to describe the properties of amalgams defined on abelian groups. And then I said, you know, I've never dealt with abelian groups. Maybe I should read something before. And his answer, as far as I remember, was, well, you don't need to read anything. The only thing you need to know for the proofs is that the sum of the two groups is a group. That's it. Go to work. All right. The second tool that we needed was a generalization of implicit function theorem. The reason why we couldn't use the existing one is, again, because we wanted to have a theorem that would apply to a whole set of spaces, right? Spaces that will be indexed by lambda, by this exponential, right? That can be used to multiply the variable so that it will, to multiply the function so that it will be in the LPQ space. Of course, what you could do potentially is to use the implicit function theorem formulated for every given lambda. Okay, and then as you remember, probably right, I'll draw the same picture that appeared here already, right? So if you have your exogenous variable here and say your endogenous variable here, right? The implicit function would give you the function in some neighborhood of the original equilibrium. Okay. So you could apply your implicit function for every given space you work with, for every value of lambda, and then of course what you need to do is to take the intersection of all those neighborhoods for which the implicit function theorem works. But given that the set of lambdas is an interval, you could very well end up with intersection being just one point, and then there's no theorem. Okay, so there had to be a new formulation for that. Okay, so the final formulation, which is roughly as it stands right now, takes out formulates defines an equilibrium again as a fixed point system. This time we start with K because if you take E, the exogenous variable, to live in L infinity 1, then equilibrium forces consumption, capital, output, and this net interest rate to be uniformly bounded functions which are continuous. And equilibrium forces also investment to live in L infinity 1, so we don't need to force it to be uniformly bounded either. Okay. And it's more convenient to work with this map from C infinity across L infinity 1 to C infinity, as opposed to the other one, where I is the control variable. And this type of fixed point will be an equilibrium if it satisfies, in addition, the set of inequalities, saying that investment and hence capital is positive. Some of the produced output is used as consumption. That's the non-stationary equilibria. And it also describes Bell's growth equilibria when endowment is equal to 0. Okay, so the first type of equilibrium is our status quo, from which we start, and the second type of equilibrium will emerge as we change the endowment in the economy. So it's not necessarily stationary; it shouldn't be. Okay. As you know, as the initial argument goes, if you pick a balanced growth equilibrium, there might be several, but assume you have a selection device. There's a finite number we show. The implicit function theorem would tell you how to find the derivative of the equilibrium variable, say k, with respect to a change in endowment, e. And as sort of basic intuition would say, it would be a composition of the two maps. The first one is the inverse of f with respect to k, and the second is the derivative of f with respect to the exogenous variable. Okay? All right. So again, to use the implicit function theorem, one has to show that the derivative of f with respect to k is generically invertible, and using the general version or more general version of the Wiener theorem, this basically reduces to verifying that Fourier transform of the upsilon decay never turns unity. Okay. So one could plot some spectra of this operator. The spectra contain all the values for which the operator minus that that number times identity is not invertible. It's in the complex plane. Of course, the graph is symmetric around the real axis. And, you know, first of all, what you see is that it's a line. So there's a hope that if by mistake or by chance the line passes through 1, 0, right, it wouldn't if you reparameterize the model. So we had a lot of fun drawing these graphs. By the way, as you see, this one happens to be inside a unit circle. So sometimes this fixed point map is a contraction. Sometimes it's not, as in the first case. So can be anything. Okay. So the one of the sort of lemmas, if you wish, says that if you pick a generic economy, generic once again in the sense of in the space of parameters, and you look at the convolution kernel of this derivative operator at a given VGE, at this particular VGE, and then the Fourier transform of this kernel doesn't contain 1. So we can use implicit function theorem. Okay? Now, we wanted to push it a little bit further, as you remember, because we wanted to use basically one implicit function theorem to show two results, both the regularity, the fact that equilibrium variables are smooth as functions of exogenous variable, and also that they converge fast enough, right, that there's this exponential convergence. For that, we needed to have a unified version, right? One of the necessary conditions was to have that inverse df/dk to be the same for the whole set of spaces. Okay, and to assure that, we had to push a little bit that first statement. And instead of Fourier transform, to take a Laplace transform of tau. Okay, so basically pre-multiply Fourier transform by an exponential. And ask the question, how far can you push this exponential away from 0 to still get, to still make sure that the transform does not return unity. Okay, this would define the range of lambdas around 0 for which our derivative operator will be invertible, and it will have the same inverse in the intersection of Wiener algebras, which are L1s with unity being epsilon Dirac at 0. Okay. Well, you can now also look at it sort of to visualize this interval. We took several parametric examples and calculated this interval around 0 for different parameters of the models. What I wanted you to take from this is that this interval indeed is open around 0, and apart from some pathological cases, non-generic parameterizations of the economy. Okay, so there's a an easy algorithm to make this calculation. Okay, so now we come to the results. The first one says that if you look at the system, the fixed point system that I described to you in one of the last slides, then if you take a perturbation of endowments in an open ball around 0 in L∞1 norm, then your resulting equilibrium will be close to the baseline in the appropriate metric. Okay? So this is the sort of the candidate regularity result. Okay, again, an open ball is an L∞1, and this is sort of a standard first part of implicit function theorem. Okay. To formulate the second part, we'll need a little bit of notation. If you remember, this is this lambda interval around 0 that we're talking about, and this would be the norm used for kernels that will describe derivatives in the system. Most of the derivatives is given by the kernel up to several jumps. As you see, it's a uniform metric, and the requirement is that it would be uniformly bounded once multiplied by a sum of extreme exponentials. Okay. So the second part of the implicit function theorem is the differentiability statement. It says that not only the implicit function exists, but it's also differentiable with respect to changes in endowments, changes in parameters. And in fact, there's a little stronger statement here. The first bullet says that the map from the exogenous variable E to the derivative of the equilibrium map with respect to E will be Lipschitz from the space where the perturbations live, L∞1, to that space where kernels are, which was described in the previous slide, for the values of the key equilibrium variables. Okay, and as a corollary from this result, you can get a very interesting statement that not only the initial equilibrium is close to the status quo, but also if you take two perturbations that converge exponentially in the neighborhood of 0, okay, the resulting two equilibria will be close to each other in the appropriate metric. Okay, so I thought that was really a neat result, and part of it came from the Lipschitz property of that derivative, which was inherited through implicit function theorem from the properties of the derivative of the equilibrium map. And if you impose additional restrictions, remember we were talking only about candidate equilibria that solve the fixed point system, and there are additional restrictions that assure that consumption never goes to 0. The same kind of theorem applies to equilibria. Okay, that also satisfy the inequality requirements. And just a few words, maybe about welfare. This is partial result. Okay, it's not complete, but just to give you a sense of sort of the beauty of the initial calculation. Remember, when we were calculating the derivative of endogenous variable with respect to exogenous variable, we needed to calculate Fourier transform or Laplace transform later of the corresponding derivatives. And because all these derivatives are convolutions, in fact, Fourier transform can be decomposed into very easy elementary blocks, right? It's a product of elementary Fourier transforms. So, in fact, we can analytically calculate the response of equilibrium variables to the changes as a result of changes in exogenous variable. And what we have from that calculation is the Laplace transform of the derivative. And in fact, when we are to calculate the derivative of welfare, all we need to do is to calculate, just by definition, the Laplace transform of the derivative of welfare, because it's a weighted sum of utilities, of changes in utilities. It just falls into that definition. So, in fact, as a byproduct of this calculation, we have an explicit formula for welfare, and it has, in fact, a very simple form. And we came back to the same formula that we had at the very beginning. in the very first result that I showed you, that indeed it's exponential. The time component is exponential, and the other component, right, is just the weights. Corresponds to weights across ages, people alive at that point in time. Okay. Well, that's about it.
Any questions? Yes, sir.
We use variables of time and age.
Okay, and then the idea there was to choose the simplest possible model to work with. Okay, so the time everybody in that economy lives for just a unit interval, right? They know exactly how long they're gonna live. So, 100 years, okay? 100 years, okay? Yeah. Mm-hmm. Yes.
Yes.
In your previous slide, you had RU, which is
Oh, yes, sure. Again, this is an application of relative utilitarianism. It's a relative utilitarianism approach, once again. It's the idea is that once you have changes in equilibrium variables, they affect individual utilities. Individual utilities then are normalized between 0 and 1, and it's the sum of normalized individual utilities that we're calculating derivative of here. Okay.
Any further questions? So thank you very much, Professor Rubinchik. And thank you. And thank you, Professor Mertens.